All right, good morning, everyone. We'll start in about a minute or so here. So. Okay, I think we're gonna go ahead and get started. So got a full day today, to be sure. A lot to go over in the lab. So we'll spend a lot of time talking about the generalized linear models that we've been discussing this week as part of the lab in both Stata and R. Everyone has received homework number 5 back at this point, and the homework number 5 solutions have been posted. So for the most part, everybody did a good job, but there were a couple common issues that came up repeatedly, and they were largely related to interactions. Okay, so including interactions in models, what's necessary to test interactions, and topics such as that. So I wanted to start today just by revisiting some of the key points about interactions and interpreting the coefficients associated with interactions, because these are the points where people got tripped up most consistently on homework number 5. Okay, so first point about testing interactions, remember something that we've talked about repeatedly in class. When you're testing individual predictors in a regression model, I don't care if it's linear, logistic, whatever the case may be, whatever model you're fitting, okay, it doesn't matter what the model is. When you're testing interactions in that kind of model, and you start by including predictor variables by themselves in the model, age, gender, weight, socioeconomic status, whatever the case may be, you have this initial model that has all these predictors, and some of them may not show up as significant in that full multivariable model that includes all the predictors. And the common issue that was coming up with the homework is that at that step, you identify a certain predictor as not being significant. Many people were just tossing it from the model, okay? When the remaining parts of the homework were asking you to test interactions involving the different predictors in the model. Just because a predictor does not show up as significant by itself in a regression model does not mean that it could be involved in a heavily significant interaction. Okay, this was one of the points that people got tripped up most by. If a predictor shows up as not significant by itself before you start testing for any interactions, it does not automatically mean that that variable will not be involved in any interactions. Okay? And I've drawn a picture to illustrate this point on the screen. Okay, so take a careful look at this picture on the screen. Let's just say we have linear regression. So we're modeling the mean on some dependent variable y. You have a predictor variable age, and let's assume that age has a linear relationship with the dependent variable y. If I was to fit a regression model that just had age and just had gender by themselves in the model, would either of them be significant given the data I've shown on the screen? Again, no interaction. If I just include age and just include gender in the model as 2 predictors, would either of them be significant? What do people think? By themselves?
The interaction.
Here's what the overall relationship of age is going to look like. Is that a significant coefficient? Are males and females going to have different means based on these patterns? Again, if I just include the predictors by themselves, no interaction, will the males and females have different means? This is going to be the mean for males. This is going to be the mean for females. No difference. So I would fit an initial regression model given these data that includes age and gender, simple as can be. Neither one of them will be significant. Would it be the right decision at that point to kick both of them out of the model and start over and say age and gender have nothing at all to do with this outcome? Would that be the right decision? What's actually happening here? There's an interaction. If you're a male, there's a big positive relationship with Y. If you're a female, on the other hand, there's a negative relationship in exactly the opposite direction. For males or females individually, that relationship is significant. Okay? there's a prominent interaction that's evident in this pattern of data that I'm showing here. And if you made the decision based on a simple model that just includes age and gender, to toss them both out of the model like they're irrelevant for this dependent variable, we're making a massive, massive mistake. And that was the point of the whole. Okay? Just because a predictor doesn't show up as significant by itself doesn't mean that it won't be involved in an interaction. Okay? That's a very important message to keep in mind. Now, maybe you're not interested in testing interactions. That's fine. But if your goal is to evaluate interactions to answer a research question, this is the kind of mistake that would be made in that situation. So when you're first getting started with the model and you're just including predictors by themselves, okay, think very, very carefully about whether you're going to kick a predictor out of the model entirely just because it's not significant by itself. If there's any possibility that that predictor is going to be involved in any interactions, it should stay in the model, even if it's not significant, which is exactly the case that I'm drawing here. Okay, everybody clear on this point? Okay, so let's keep building on this example with what you were seeing in problem 8.4 then, which is another place that a lot of people got tripped up with writing plain English interpretations of those interaction coefficients. Okay, so, your question.
The recommendation of seeing the relationship between variables before analyzing the model. And when you do the first step, putting the testing the significance of the effects, it's just to give you an idea about the picture.
Yeah.
Okay. But you always try to test the interest.
Yep. Yeah. Those initial bivariate tests tell you zero.
Yeah.
About interactions. Zero. Yep. So it's a first check on the data, if nothing more. Okay. So based on the graph that we're seeing here, let's suppose that the dependent variable goes between 0 and 10. Okay. All right. So I fit a regression model to these data. My model is y equals an intercept plus a coefficient times gender. Let's suppose it's an indicator for being a male, plus a coefficient times age. And that would be my massive mistake of a model right there if I just stop there, right? Okay. Plus a coefficient for the interaction between the male indicator, which is just 1, 0, and age. Okay. Okay. So let's just test your guys' knowledge of what we're seeing in this picture. Okay, given that y ranges between 0 and 10. Here's our coefficient. Here's the estimated value of that coefficient. What is the estimated value of beta 0? Not a trick question. This is something you guys should be comfortable with at this point. Okay. Who can tell me what beta 0 means in plain English in this model? Age is continuous. Male is a 1, 0 indicator for being a male. What's the plain English interpretation of beta 0?
Actually, it doesn't mean anything because
No, it's definitely got a meaning in this model.
age equals 0. Oh, okay, it means something.
Let's assume age equals 0 is meaningful.
Yes, mean being female, it will be equal to this.
Yep. So it's the expected value of the dependent variable at age 0. Let's say this is 0 here for being a female.
Yeah, it would be the 1 unit or one from age birth to would be the default. So at birth for females, the the average level of Y at birth
Right.
for,
Right,
it
so
is.
what is the actual value of the estimate? That's what I'm asking. So I have to look for females at age 0. What is the actual mean?
and
10. Okay. The intercept is not an overall mean. It is a very specific mean when all the predictors in the model are equal to 0. Right? Okay, so we're talking about the mean at birth, if you will, for females. Okay. What about beta 1? Let's start with the plain English interpretation of beta 1. What is beta 1?
mean at birth for males.
Is it the mean for males?
No,
What is it? You can tell me what beta 1 means in plain English. Remember, you guys are going to be writing up this kind of stuff.
Female is the reference.
No, female is the reference,
Yeah.
right? Because we have an indicator for male in the model. So what is beta 1 telling us?
It's not a male. When the age is 1 year.
Not when age increases 1 year. What are we getting for beta 1? Okay, Gladstone had half of it. So it's the change in the mean for males relative to females when? Not for a 1 unit change in age. That was the mistake I'd say 50% of you made on the interaction. Okay. Beta 1 is the change in means for males relative to females. It's not a change. Beta 1 is the change in means for males relative to females when? When age is equal to 0. When the other variable involved in the interaction is equal to 0. Remember that when that interaction is in the model, those lower order terms are conditional on the other variable being equal to 0. Okay, so I know this is the difference in means for males relative to females, okay, when age is equal to 0. So if I look at my graph, what is the estimate of beta 1? Let's say this line goes all the way down to 0, and this line goes all the way up to 10. What's the estimate of beta 1?
10.
Is it 10?
Minus.
It's minus 10, right? That's the change in the mean. The mean for males is about 10 units lower than the mean for females when age is equal to 0. Okay, because I have that interaction in the model. If I were to take out beta 3 and take out that product term, different story. Okay, because I have that interaction term in the model, that changes the interpretation of my lower order coefficients. Makes them conditional on the other variable being equal to 0. Okay, same exercise. What's the plain English interpretation of beta 2? We're not talking about odds. It's a linear regression model, so we're talking about a mean. Difference according to what? Not odds. We're not talking about odds. Unit increase in age for females, right? Thank you, Jupiter, right? So again, we're talking about the change in the mean of the dependent variable as age goes up by 1 unit, okay? Not overall, when the other variable involved in the interaction is equal to 0. In this case, that means being a female. Okay, we're conditioning on the other variable involved in the interaction being equal to 0 when we interpret these lower order terms. So it's the impact of a 1 unit change in age specifically for females. Okay, so looking at this graph, just to make it simple, suppose the span of that line was between 0 and 10. Okay, what would be my estimate of beta 2? 10. As age goes up by 1 unit, roughly speaking, what happens to the mean of Y for females? If I go from 0 to 1 in age, what happens to the mean for females? Goes down by about 1, the way I've tried to draw this, right? It's a square. Okay, so my estimate of beta 2 minus 1. Okay. Now let's turn to the interaction. Okay. I've established these conditional interpretations of beta 1 and beta 2. So let's suppose that our goal, our research objective, is to talk about how the slope of age changes for males relative to females. Okay, that's our objective, because you can look at this interaction both ways. It could be the change in the male effect as age changes, or it could be the change in the age effect as gender changes. Let's say we're interested in the change in the age slope as gender changes. Okay, so what's our plain English interpretation of that beta 3 coefficient? We already know that beta 2 is the slope for females, right? So what's beta 3? What's that word I said that you automatically have to have enter into your mind the minute, the second that you look at an interaction for a coefficient? Change, right? So if we're focusing on the change in the slope, what is beta 3?
Beta 3 is got to be positive because it's beta 2, the age would be looking at, by default, if you're female, as you go increase, if your age increases, the line obviously is going down. So your Y value is more likely to go down. So for male, it's got to go up, as it would be 1. Easily just.
Well, if it was 1, Sarah, think carefully here. If it was 1, the slope for males would be 0. Right? Because remember, beta 3 is a change relative to what that reference category was, which is females. Okay, what do we see in the picture? What's the slope for males?
Positive.
1.
1.
So what's the change?
2.
2. Right? So the estimate of this interaction coefficient is 2, because that's the change in the slope for males relative to females. Okay, the big mistake here, that is not the slope for males. That is the mistake that you 100% want to avoid when interpreting models with interactions. Okay, first word that enters your mind is change. And based on the interpretation that we wanted to make, beta 3 is telling us how that slope changes for males relative to females. Okay. Leah?
What will happen if we added beta 3 to beta 1 and beta 3 to beta 2?
Well, beta 3 to beta 1 would give you the overall slope for males, right? So beta 2 plus beta 3 is going to give you the net slope for males, which is what we just said was 1, right? We're taking -1 plus 2. That yields 1, which is the slope for males.
And beta 3 to beta 2.
That's what I just said. Beta 3 to beta 2. Beta 3 plus beta 1 is telling you how that gender effect changes as age goes up by 1.
And
Remember?
the other one is when for females. It's for males. And beta 2 plus beta 3.
Beta 2 is for females only, right? Because that's the 0 value of the other variable involved in the interaction.
My question is that when we interpret, we are interpreting for females only. Because if we added beta 3 to the coefficient, it would be the other way around.
It'd be the slope for males. Because beta 3
applies for adding beta 2 to beta 3.
Yeah, beta 3 is a change. And remember, you can just plug in values into this equation to check your thinking, right? If I set m to 1 in this equation, my regression equation is going to be y equals beta 0 plus beta 1. That's my intercept. If m is equal to 1, plus beta 2 plus beta 3 times age. right? I'm just literally plugging in one to the equation. So if I'm a male, that's my slope. I have a slope of 1. I have a mean of close to 0. Okay. If I fix m to 0, meaning I'm talking about females, so this is for males. If I set m to 0, I get y equals beta 0 plus beta 2 times h. Right? So writing it out like that in terms of the equations, I instantly see what beta 1 and beta 3 are. Changes for males relative to females, right? This is the exact exercise you want to go through every time that you interpret an interaction. Because again, the scientific insight can be very large. Here I'm seeing there's a completely flipped relationship of age with Y depending on what gender I am. And I would completely miss that if I had not tested this interaction. Okay? But we got to be careful about how these get interpreted. Okay? So questions about this example, those were the main issues on homework number 5. People pretty much nailed everything else with respect to logistic regression. Okay? Just got to be very careful about these interactions. Very powerful tools, but it's a challenge to interpret them, and we just have to take it piece by piece. Okay, okay, questions, comments, thoughts on homework number 5 or anything we've talked about here related to interactions?
It's a question.
Yep.
So is there a systematic way for us to figure out any kind of interaction terms in our model when it comes to categorical predictors?
Same approach now. Got to go through the same approach. Each binary indicator that you're dealing with, same exercise. Okay, that's the systematic approach you should take. We've established how to test for whether interactions are important. So that's the first step, is to show that it's worth going through everything we just went through, right? If I went through everything we just went through, and the Wald test for testing this interaction between age and gender had a p-value of 0.75, it's a complete waste of 25 minutes, right? So step 1 is to use that Wald test to demonstrate that the interaction is adding something to the model. Step 2, if it is, we go through this interpretation. Doesn't matter if we're talking about dummy variables, continuous variables, same systematic approach. Writing down the coefficients, writing down what they mean, making sense of them.
Thank you.
Okay. Other questions about this? Okay, so some of you may want to test interactions on your project, some of you may not, that's fine. But just remember, this is the kind of systematic thinking that we have to go through when thinking about interactions. Okay. Okay. Hang on to that. All right, let's turn to our lab session for today. All right, so our goal today in lab is to focus on examples of multinomial, ordinal, and Poisson regression analyses. Okay, so at this point, again, all the stuff that setting the survey design features, data management, I'm going to go through that very quickly, because I want the focus to be on the model fitting and making sense of what we're seeing when we fit these kinds of models. Okay, so that's going to be our primary focus. And as usual, the lab is listing all the key procedures that we're going to be talking about as part of the lab session. Okay, so let's start with Stata. I've copied the lab notes for today, lab 6, into a Stata do file editor. So I'm going to read in the data, start a log, and rename everything to be in lowercase and set my design variables. Specifically for NCSR, I want to use the long weight, okay, given the predictor variables that I'm using in the multinomial model. Okay, one of those variables was measured in the longer part of the survey that was only given to a subsample. All right, so that's why I'm choosing the long weight in addition to the other design features. All right, so I'm executing all of that at once. That's strange. I don't know why I'm getting an error about my log file, but that's okay. That's good. Okay. So I have the design variables set, got the data set read in. All right, for the multinomial model in Stata, remember the command that we would use is SVYM-logit. Right? Dependent variable in this case is going to be working status, like we talked about in lecture. And then as predictors, we're considering age, sex, having a major depressive episode, and education category, with category 4 of education set as the reference. All right, so I'm using IB4 specifically to set category 4 as the reference category. All right, then specific to multinomial modeling, I'm choosing category 3 of the dependent variable to be the reference category for setting up the logit functions. So I'm going to have 2 logits, 1 versus 3 and 2 versus 3 with this choice of an option here. Okay, remember, we have the flexibility to do that. And then with the RRR option, I'm asking for odds ratios for each of those 2 logits. Okay, so this is the command I would use to fit that multinomial logit model. I'm going to go ahead and execute that here. Okay, it's going to take a little second. Okay, these models take a little bit longer to fit because remember, there are so many parameters that we're estimating. We're estimating all those coefficients for each of the logit functions that we're modeling. Right? So it's going to be using maximum likelihood estimation, calculating those estimates, calculating the linearized standard errors, and then converting them to odds ratios via that RRR option that we're using here. Okay. Okay, now what I want to point out about this data output that gets generated when you fit this model, notice how it labels the output by the non-reference categories of the dependent variable. So these are the odds ratios in the generalized logit function for category 1 versus category 3. These are the odds ratios in the generalized logit for category 2 versus category 3. 3, by choice, was set as the reference category for the dependent variable. That's how we're defining our logits. Changing the reference category would not change anything about the fit of the model. It just changes our interpretation because we're looking at different logit functions. Okay? So all this boils down to is 2 exercises in interpreting logistic regression coefficients. Okay? We don't have any pesky interactions to worry about in these interpretations. Right? And I've converted everything to odds ratios. Stata is again labeling these as relative risk ratios. That's what that RRR means, but it's exponentiating the estimated coefficients. Okay. So if, for example, we look at the relationship of age with the odds of being in category 1 relative to category 3, so employed versus not in the labor force. Okay. We would say that as age goes up by 1 unit, because it's continuous, the odds of being employed relative to not in the labor force go down by about 4%. Because the odds ratio is 0.96. Okay, just logistic regression at that point. Okay, nothing different from what we talked about. We're just talking about 1 versus 3 on the outcome. Okay, what about gender? Here the odds ratio is 1.8, let's call it, rounding up. So if I'm a male relative to female, the odds of being employed versus not in the labor force, they go up by about 80%, multiplied by 1.8. Now, why would males have such higher odds of being employed as opposed to not in the labor force? Why would that be? Why would males have such higher odds of being employed as opposed to not in the labor force? What's making females of an adult age more likely to not be in the labor force? What can females do that males can't do?
Responsibilities of kids.
Have kids. So there's gonna be this kind of gap to begin with, okay, for adults who want to choose to have children. Okay, females are gonna have to go through pregnancy, give birth to the kids. Hopefully they're working together with the kids, but the females are less likely to be in the labor, to be employed. Okay. What about major depressive episode? Does it make sense to interpret that odds ratio? Yes, no? We want to go through that effort? Why not? Why not? Not significant. Okay, assuming that MDE is not involved in interaction, it doesn't matter in this logit. Okay, might be a way to simplify the model. All right, let's look at 2 versus 3 just as some examples. Okay, what about age? Okay, we saw age had a kind of a negative impact on the odds of being in 1 versus 3. What about 2 versus 3? Unemployed versus not in the labor force. What happens is age goes up by 1 unit. Not significant. If we're using a strict 5% level, no point in going through that exercise, right? Okay. What about gender? If I'm a male, what happens to my odds of being unemployed versus not in the labor force? They go up by half or they go down by half?
Down.
Right. The odds ratio is 0.5. So I'm cutting the odds in half if I'm a male. They go down significantly, the odds of being unemployed versus not in the labor force. So that's interesting. It's saying that males are more likely to be not in the labor force than unemployed. Because that's the logit that we're talking about when we compare 2 versus 3. Okay. So 2 different logit equations define this model. It all defines one larger model that allows us to calculate predicted probabilities. But we just have to treat this like 2 exercises in binary logistic regression when going through the interpretation. Okay. And these are our weighted point estimates with 3 as the reference category. Now, because there are so many coefficients, there's a variety of different Wald tests that we can do, design adjusted Wald tests. Here, this particular test is testing whether sex and education category matter at all as a block of predictors in the overall model. So remember, this is not going to be a test with 4 degrees of freedom in the numerator. This is going to be a test with 8 because we have 2 logit functions, right? So there are that many coefficients in each of the logit functions. So the overall test of importance, we're actually testing 8 parameters, okay? Now, notice because there's so much being juggled in this particular case, in the multinomial model, Stata is showing you all the possible parameters that might be estimated, but all of the coefficients for logit or for category 3 are dropped out of this test. That's why they have a little 0 next to them, just because that's the baseline category of the dependent variable. So there's no coefficients associated with category 3. So although it looks like there's 12 parameters, 4 of them are being dropped. As you can see here, it's saying constraint 3 is dropped, constraint 6 is dropped, etc. So in the end, we have a test with 8 degrees of freedom. Those are the 8 coefficients that are being tested. And what would be our conclusion based on the results of that test? What's our decision? Are these blocks important to include? Yes. At least one of those 8 coefficients is different from 0. Not all of them, but at least one of them. Okay. So it seems like there's definitely some action there. That's a very broad test because it's across both logit functions. Okay. Here's the overall test for all of the parameters that are being estimated in the model. So there we're including age, gender, MDE, and all 3 of the non-reference education categories. Okay. So if I do this test, okay, 12 parameters now being tested. It's clear that some of them matter. Where else in the Stata output am I going to see that exact same test?
The statistic in the expression.
What's that, Sarah? Say again?
The F statistic in the initial regression.
Right. So if I go all the way back up here, spread this out a little bit. There it is. So again, Stata by default is showing you the overall design adjusted wald test that any of the predictors in the model matter. So especially in a multinomial logit model where you have double or triple the number of coefficients that you're usually trying to estimate, if that test is non-significant, it's really back to the drawing board. Because that's saying that there's not a single coefficient in any of the logit functions that's different from 0. Okay, nothing is happening in terms of your prediction. Okay, but that's the overall test of all the coefficients across both logit functions. That's what's being printed by default. Okay, so that's an automatic compute. One thing that people fitting multinomial logit models might want to do is test that a given coefficient is the same in both of the logit functions. So that's another thing you can do with the test statement, is say that education has the same effect on both of the logits. Okay, and that's what this syntax in square brackets 1 = 2 is doing. It's saying, are the coefficients for education as a predictor the same in logits 1 versus 3 and 2 versus 3? Okay, that's what that 1 = 2 means. Right, so we can perform this test to see if that holds. Right, so notice the way the hypothesis test is being written. Okay, 1 is the difference between the coefficients for logit 1 and logit 2 for education category 1. 1 is the difference for education category 2, and 1 is the difference for education category 3. Okay, so in the end, we have 3 degrees of freedom, 3 contrasts that we're testing there. Okay, and we would reject the null hypothesis that all of those coefficients are the same. It's clear that the education effects are differing across the logits. So if we go back up, look what happens. It's not entirely surprising. Right? Lower education categories, less likely to be employed. Lower education categories, more likely to be unemployed. Okay? Very different relationships depending on what logit we're talking about. So not surprising when comparing those two. Right? Another variation of that wald test. Give me a wald test for the effect of a particular predictor in just one of the logits. So not across all the logits, but just one in particular. So this second test here is saying, does education matter when you're predicting the odds of being unemployed relative to not in the labor force? Okay, we're getting that by using 2 in square brackets. That's referring to the second logit function in this particular case, okay, which is 2 versus 3. So we can go ahead and run that. Now, what's the conclusion of this test? Say again louder. We're going to reject, or we're going to fail to reject? Fail to reject, right? So we would fail to reject the null hypothesis that all 3 of those coefficients in the second logit, not overall, but in the second logit, are equal to 0. So what that means is that education doesn't matter when predicting the odds of being unemployed or not in the labor force. Okay, even though it looked like everything was in a different direction, if we go back and look at the actual test of significance for the individual parameters, look at what we see. Okay. So education does not seem to matter for that particular logit, but because it matters for the first logit, we would still keep it in the. Okay, everybody with me so far on the wald tests? So these are all different flavors of wald tests for multiple parameters that you can consider. We just have to remember that in a multinomial logit model, there's several logits to consider. So a lot of these tests are going to have more parameters than we're used to. Okay. Now, another thing we can do in terms of diagnostics for the multinomial model is test for goodness of fit. Okay, so the mlogit GOF command that we talked about in lecture, also talked about in ASDA, this is not a base Stata command. Okay, this is a user written command. So if you've not already installed that previously, we have to install it first and then execute the command after fitting a particular model. So if you don't already have that a particular user written command like this installed, you can say find it mlogit GOF, or whatever the name of the command is. And that's going to bring up whatever Stata help files are associated with that user written command. Okay? So we see that this command was actually provided as part of a Stata journal article by Fagerlund and Hosmer. Okay? And they've provided a link to the code that will carry out this goodness of fit test. And you follow that link. Okay? So if I follow that link, then it says, click here to install. And because it's a user written command. So I'm going to say, click here to install. Okay? And it will install the code to make that command available as part of your analysis. And we also saw this with EPC tile, right? That was another user written command for percentiles. Okay? So now that we have mlogit GOF available, I'm going to refit the model. And then after I fit that model, same output that we've already looked at, all I have to do is run that single command, mlogit GOF. It's kind of like margins plot, estat GOF. Okay? Now, same way we looked at this for goodness of fit for logistic regression, the null hypothesis is that the model fits the observed data well. Okay, so what decision do we make about that null given this result? Right, model's inadequate. Right, we're rejecting the null. It says we still have some work to do because those predicted multinomial probabilities are not lining up with the actual multinomial outcomes. Okay, so what a model that fits well, if my actual work category is 1, and I look at my 3 predicted probabilities for work category, I got to have the highest probability in 1 and very low probabilities in the other 2 categories. That's what this is getting at. Okay? So what this is saying is that there's plenty of people with a 2, for example, whose highest predicted probability might be 1 or 3. Okay, so it's saying we're missing some predictors, or there's something else we have to consider that we haven't yet to try to improve the overall fit of the model, because a significance test of 0 with a p-value of 0, not a good result when we're testing for model fit. Okay? So if you look at these predictors and we're talking about employment, we're talking about age, gender, whether you've had a major depressive episode, and education. What else might predict employment that we have not included here? What else might predict whether or not you're employed? Could be interactions. What other predictors?
Race, which
Race.
probably means other things, but still.
What else?
Your health status.
Health status, right? Physical functioning, physical health, mental health. Okay. We don't have a single control in this model for any kind of health status. Right? We have age, but we don't have any indicators of health status in here.
You also
Right?
don't have indicators of like region or anything that looks at the local economy where you're living.
Geographic information, right? So we're not trying to pretend that these are all the predictors that might matter for your employment status. But this is the exercise, right? When you see a goodness of fit test with a p-value of 0, we're back to the drawing board with the predictor set that we're using, because it's not yielding predicted probabilities that are consistent with the observed data. Okay. So it would definitely be back to the drawing board in the case of this particular model.
Okay.
Yeah.
So what value should you expect for
Anything above 0.05 or 0.1, whatever significance level you're using. We just don't want the test to be significant. I mean, if you saw a p-value of like 0.048, it's on the borderline, but this, we got to go back to the drawing board. Okay. Okay, any questions about those interpretations for the multinomial model? Any questions about the coefficients, the wall tests, the way the output is presented, the goodness of fit tests? Any questions about any of these elements of the multinomial model? Very good. Okay, let's move on to ordinal. All right, so in Stata, the command that we want to use is O-logit. Okay, so SVY O-logit by default fits that proportional odds model, where we have a common set of regression coefficients for any cut point that we choose for that particular dependent variable. And remember, Stata is using that negative parameterization. So a positive coefficient means that you're more likely to be in higher categories of the outcome. We always have to keep that straight before we start interpreting the results. So what we're looking at here is a 6-category predictor of obesity status. And if you look at the variable list, it's a reordering of BMI. Okay, where 1 tends to be individuals with the lowest BMI, and then increasing categories represent higher levels of obesity. Where category 6 is kind of maximum obesity. Okay, that's where there are significant health concerns. Right? So this is a recoded version of BMI into these 6 ordinal categories. So that being said, how many cut points in the ordinal model are we going to be estimating in this case? 5, right? We need 5 cut points to estimate 6 probabilities under the logistic distribution. Okay, good. All right, so in this model for ordinal obesity status, I'm considering age, gender, race, and having a major depressive episode. Again, could certainly be others, but those are the 4 that we'll start with. And I'm asking for odds ratios to help with my interpretation. The odds of being in a higher category versus a lower category. All right, so let's go ahead and estimate this model. And pseudo maximum likelihood. Right, so again, you just have to appreciate what you see in the output for these kinds of models. We talked about in the multinomial model how you see separate logits relative to a baseline category. Now we're seeing common coefficients across all the categories, but different cut points. Okay, taking advantage of the fact that this is an ordinal measure. So it doesn't matter what cut point we choose, we're still going to be able to calculate a predicted probability, but the predictors matter in the same way. Doesn't matter what we call high and what we call low. Okay. So keeping in mind Stata's negative parameterization, okay, let's just look at being a male, for example. Okay, I've gone on and on about how males don't take care of themselves. Right? So the odds ratio for males is 1.54. And remember, with Stata's parameterization, we're modeling the probability of being in higher ordered values, which means more obese. Okay, so what's our interpretation for males, given this odds ratio? How would we say this?
The odds of,
Go ahead.
the odds for dependent variable is
The odds of the dependent variable being what?
1/6.
Remember though, we're just talking about higher or lower values for ordinal regression. Okay. So given Stata's parameterization, we're saying the odds of the dependent variable being higher, which in plain English means being more obese. So the odds of being more obese are
Is 1.5 times for males,
1.5 times what? Higher or lower?
higher.
Higher for males relative to females, right? Or 54% higher. So the odds of being more obese for males, 54% higher than they are for females. What do we mean by more obese? In the proportional odds model, it could be 6 versus the other 5. It could be 5 and 6 versus the other 4. It could be 4, 5, and 6 versus 1, 2, and 3. It doesn't matter. We would make the same interpretation. However, we cut off higher versus lower. That's the proportional odds assumption. Okay, so that's what we're seeing here. We are going to test whether or not that holds for all these categories. Okay. What about for, let's say, MDE? Okay, people who have ever had a major depressive episode. What would we conclude for them? By how much?
25%.
26%. So the odds of being in higher BMI categories, the odds of being more obese go up by about 26%. Okay, so a positive coefficient or an odds ratio above 1 mean that you're more likely to be in a higher value category for Stata users. Okay, That's always the key thing to remember is how is your software parameterizing these models? The cut points themselves, not of a ton of use just to make these interpretations, but they are useful to calculate predicted probabilities under the logistic distribution. So that's the information we would use if we want to calculate predicted probabilities. And Stata's predict command does that automatically for us anyway. Okay, so Stata still shows these estimates, but interpretation purposes, they're not particularly useful. Okay, wall tests work the exact same way. Now we don't have multiple logits. We're just testing whether either of those two predictors here are significant. So if I test MDE and sex in the same way, clearly we conclude that these are at least one of these coefficients is different. And we just went through both interpretations, so we know that going in. Okay. So not a surprising result there, but still important to conduct those tests. All right. Now, if you don't want to see odds ratios, remember you can just take out that OR option. Okay. So that'll give you everything on the log odds scale of being in that up to and including a particular category, but we're being on the minus contrast for Stata in this case. So positive coefficient, higher probability of being in higher categories. If you get confused, remember the strategy is to just fit the linear regression model to the same ordinal outcome. Same model, same predictors, just to make sure you're getting the directions right. Okay. So all I'm doing here is I'm changing the survey command to regress. Right? Everybody see that? So I'm using linear regression for that ordinal variable. A lot of people do this anyway. Like they don't fit the ordinal model to begin with. They just treat that variable like it was continuous. And they model means that. But let's look at that output. So using weighted least squares, fitting a model to that ordinal dependent variable. Now I can just say what happens to the mean on that 1 to 6 scale as these predictors change. So I can say, as age goes up by 1 unit, the mean gets larger. By a small amount, but that's just 1 unit change. If I'm a male, the mean gets larger. I go farther towards higher valued categories on the obesity indicator. Okay. If I have major depressive episode history, the mean gets larger by about 0.14. So looking at this, I'm making sure my interpretations were correct previously based on the odds ratios. So it's always a check just to make sure you're interpreting things in the right direction. This isn't the final model we would report, but we're just using it to check the directions of our interpretations. Okay, everybody with me on that? This is very valuable because some software like SAS, for example, you'd see that the odds ratios are in the complete opposite direction of what you'd expect because of the way that the model's being parameterized. So we can always use linear regression to check and make sure we're interpreting things in the right way. Okay. Now, what I mentioned is being very cool about Stata for Stata users in class this week is this user written command called gologit2, okay, which provides all kind of cool diagnostic stuff for fitting ordinal logistic regression models. All right, but like mlogit.gof, it's a user written command. So we do have to install it before actually using it. So same process here. I'm just going to type find it, gologit2. Okay. And you can see there's been a lot of updates to this over the years. There have been a lot of Stata Journal articles about this over the years. This is everything related to that particular command. So for a command like this, where there's been all these different updates, just download the newest version, right? And so that's the newest version up here at the top. So I'm going to click on that link. Again, click here to install. Okay, make sure that installation finishes. Now I have the gologit2 command available. With gologit2, I don't even use the regular SVY command. I actually fit the ordinal logit model using this GSVY modification. Everybody see that in the syntax? So once I download and use this particular command, I start with GSVY, not the usual SVY modifier. Okay, this is the way that the newest version of the gologit2 command works for these kinds of ordinal models. The model itself looks identical, okay, the actual formula. After a comma, I've included the option called auto fit. What that means is that it's going to go through and fit every possible competing model to that proportional odds model and do all the comparisons that the coefficients are equal across all those different models. So auto fit is going to take longer to run because it's fitting all these competing models. Okay, especially if you're using jackknifing or bootstrapping or balanced speed of replication, because you're always fitting all those models. And you don't have to do that. Okay, by default, it will do all the testing, but not show you the estimates. Okay, so with that one command, assuming the survey design features have already been specified, let's go ahead and run that and see what happens. Okay. So it's going to take a sec, but I want you to watch the screen and watch what's being shown as this model is being fitted. Okay. It's going to go through, fit the full model, and then test all those possible constraints for every single predictor. Test whether or not the coefficients are equal across those different possible logits. Okay, so in this case, it went really, really fast. But this is what I mean about this syntax being, or this command being very verbose. Okay, it shows you exactly what's being tested. So it tests whether the MDE coefficients are equal across the logits. Sure. It failed to reject that. Test whether the race category coefficients are equal across the different cut points. Sure. Failed to reject all those. Unfortunately, we get to this step. It says the constraints for proportional odds or parallel lines are not holding for both age and gender. Okay. So what this is telling us is that the best fitting ordinal model is going to allow the age and sex coefficients to vary depending on the cut point. Okay. But fix race and MDE as being constants across the cut points. Okay. So depending on what the cut point is, the relationship of age with the cumulative odds may change. That's what this is saying, as opposed to the default proportional odds model where we have the same coefficient for age no matter what the category. So what that means is it matters what we call higher or lower for age. So if we call 6 versus everything else higher versus lower, age may have a different effect. If we call 6 and 5 versus 4, 3, 2, and 1 higher versus lower, the coefficient for age may change. As opposed to before where the coefficient for age was constant. And it didn't matter how we delineated between higher versus lower. Okay. So given that result, this GeoLogit 2 is going to refit the model, allowing for those possibilities. So notice now, this looks more like the multinomial logit model output. Okay. Depending on what cut point we're using, the relationship of gender with that particular logit of being higher versus lower changes. So look at category 1, for example, which is like being in category 2 through 6 versus category 1. Big positive relationship. Okay. Look at category 2, which is like 3, 4, 5, and 6 versus 1 and 2, and how we distinguish. Not as big of a relationship. Okay. Notice how the age and sex coefficients are changing depending on the cut point, but the race and MDE coefficients are being fixed. This is called the generalized ordered logit model. And in this particular example, it's saying that this model has a better fit than the model assuming proportional odds, fully accounting for all the complex sampling features. Okay. So when we're reporting, we want to say that the relationship of age with being higher versus lower obesity varies depending on how you make that distinction. That's the point. Okay. So this guy, very important for testing that proportional odds assumption, fully accounting for all the complex sample design features. Okay, this is really the only place that you can do this right now. Okay, so that's an important aspect of model fit when you're focusing on these kinds of ordinal models. If everything was fine and none of these tests were significant, you could just report the standard survey O logit. Because again, it doesn't matter how you distinguish between the two. Okay, everybody with me on this example, the way GeoLogit 2 is working? Okay, so it'll give you an idea of whether or not that proportional odds assumption seems satisfied. And in fact, if you come down here further, you can see that we've arrived at cases where gender doesn't even matter. Like for cut point 3, if we're distinguishing between what that would be, which is 4, 5, and 6 versus 1, 2, and 3, gender doesn't matter. So whether gender matters depends on how you define higher obesity versus lower obesity. That's the message. Okay, so that's what I want to see about ordinal models. Any questions about that for ordinal models? Questions about that? Okay, more than happy to consult on making sense of those models. If you come across an ordinal dependent variable and you want to try some of this stuff out in Stata, I'd be more than happy to talk to you further about that at some point. Okay. Okay, I think this is a good place for a break. So it's about 5 after. Let's break till about 11:15. And then we'll pick up with our discussion of Poisson regression and then turn to R and see how to duplicate this stuff in R as much as we can. Just as a reminder, remember that your final overall drafts of your final projects are due on Monday. Okay, so like we did before, you can plan on taking till 5 o'clock to submit them. So don't worry about submitting them by the time class starts on Monday at 9, but try to get them in by 5 o'clock so we can begin reviewing them. So, okay. All right, let's break till about 11:15.
Confused about the new policy all the time. Also, there is no association, so I rejected the so I reject this, so there is association.
I have a question for want to discuss
has internet.
this is
But, for example,
I have set the
use
subpopulation.
internet and not
Get some
device
ideas of
is.
like,
Yeah,
the
no, but I
description is
remove
right
this
having
variable
the
and
number of
function as the
population
program.
7,000, but the subpopulation number is definitely 35,000 because we
I
are
will
not
do
having
everything.
a computer lecture. So, but I'm just wondering if the population size comes out to be the same.
It just means they have 0 weights. All those cases you're dropping out at 0 weights.
Zero weights, but the outcome we are having like it's like a live outcomes or we are.
No, it just means the weights are 0. It's not a question of reliability. It's just saying that all those cases that are not relevant for your subpopulation didn't get
I want
weights.
to understand
Whatever weight.
what is this zero? Okay.
So my question is this, we are having the subpopulation size is 30, so similar to previous one. So is this fine?
It's trying to. Yeah, I mean, that's where you have to ask the question, given what you know about this population. Are there 32.8 million people in that population?
So although we are reducing our
You have to
survey
wait till-
population size to 35,
You have
but
to
we
wait-
are having the
wait
same
till-
again population
Because of
size.
Oh, I know you're reducing the sample size because
Yeah.
all those 1,500 people.
Yeah,
All they're doing to calculate the population size estimate is summing the weights.
So we can write to this thing into the project, yeah, just to make sure that we are. I was just trying the different combinations, like they have this
But the
small-
application,
they
the
have
track
like
application is
different-
signed, but the raw Scott is.
errors upfront, because when I run this model, what I'm having like different numbers, I am having like
Yeah.
I think I can ask you that.
insignificant. Just we were talking during the lecture, we don't drop this straightforward.
If you want to interact with us.
Yeah, we need to test instruction term. So like, what is the best approach to make this variable interact with any other?
That's up to you. It's whatever interaction you want to. So you have to ask scientifically, for the dependent variable that you're looking at, what relationships might gender moderate? So does gender moderate this relationship with the dependent variable? Does it moderate this one? Does it moderate any of these? Does it moderate any of these? That's where you have to say scientifically, is there a reason to believe that gender could moderate or change the estimated relationships of all these other predictors with your binary dependent variable? That's, I can't answer that. You have to answer that based on your knowledge of this subject.
It's almost like the same.
Then, my
Yeah,
overall,
but my
based on my
point
own
is,
knowledge, I have this text
right,
with some of the
how
technical, like
Scott
more
is
associated
saying
variables
that
like economic for sure. Because these two variables are more contributing to the child labor incidence. So straightforwardly, I have removed these two indicators. That's my knowledge, and then I get the some like reasonable estimates in terms of like different, because then I tried various models like then I gathered again household chores later, and side by side I'm also testing the goodness of it as well. So this is also telling me the best approach. To what
No,
kind
I
of
imagine
things
this,
we are
but I
having.
want the whole.
Yes, there's support for using that.
Okay. So maybe I'm in the process of dealing with interaction term as well, so I will discuss over the
Yeah, again, I'm not gonna have any input on that, so you have to think scientifically, like what interactions make the most sense for this outcome. You know, where are the associations gonna change depending on combinations of these.
If we don't want to have such kind of interaction come into the model, then it's fine. Also.
Yeah, just say in your discussion that like a direction for future research would be to focus on some of these interactions, but yeah, everything you have here is.
But in this, I think.
Okay.
Desktop, laptop.
I have a question, but not on the project,
So
more of
I
the
will
class.
Okay.
So I was just curious how it's like the
This, because this is what is
geologic,
Geologia too, yeah.
the magic command.
Yeah, yeah.
It was so cool because like before I tried using proportional odds in my work.
Yep.
And finding out the partial proportional odds assumption was quite difficult in R. So what was the method in evaluating if the partial proportional odds assumption?
So it's fitting all the competing models. So it's fitting a model that allows it's one of those intermediate models that I talked about in lecture, where, for example, the relationship of MBE with the outcome varies depending on the cut point. So it relaxes the assumption that the MBE coefficient is the same across all those different cut points, and then it compares the coefficients in those two models.
Right, so ANOVA or AIC.
It actually uses a wall test. So it uses the design adjusted wall test like we were talking about. In those different logit functions, is the coefficient for MBE the same?
So it tests all the possible combinations and compares.
Right, just like we did when we said compare a coefficient as being equal in logits 1 and 2 in multinomial logit modeling. It's doing the same thing. And then it's just automatically reporting the results of all those tests.
It's like Harrell also has a method, right?
Say again, is it?
Frank Harrell of the partial proportional odds.
I'm sorry, I'm not sure what you're asking.
So like Frank Harrell has a method for assessing.
Oh yeah, there's all kinds of methods out there. The key is
This one is
what
automatic.
no, not that it's automatic, that it accounts for the complex sample design features. So it's using design adjusted wall tests to make those decisions. Yeah, all the stuff Harrell's done is great. Simple random sample. That's the difference.
Thank you.
Great.
Yeah,
Can I ask?
yeah, sure.
About our project.
Yep.
The raw Scott test. for the variables, and I know that we are using many variables about using internet in mobiles, internet desktop to predict the use access internet in households. I know this can be related, correlated, I don't know. But the problem is the raw spot said the p-value is less than 0.05 for every variable. Sure. And when I put in the model, there are this problem here. And when I put every variable in the model, there are these problems.
So it's saying that somehow one of the variables that's being specified there doesn't vary.
Yeah,
It's got values that don't vary. So the way that HH design was being created.
I think because it's so high.
Yeah.
But remember, what's happening too is that it's using list-wise deletion. So if you have missing data on these variables and the sample size has changed depending on the variable for these Rouse-Scott tests, which it looks like it might be changing for some of them, those cases are going to get dropped in the multivariable model. And if the dropping of those cases results in a case base where one of those variables doesn't change, that will produce that.
Yeah, but how I can discover what the variable?
You gotta go variable by variable, look at the missing data and see, you can create your own indicator of whether there's complete data on all of those variables. And then based on that indicator, pick out the unique features of the cases that would be dropped due to list-wise deletion.
I understood.
Yeah, so like you have, the idea would be in your complete data set, it looks like there's variability in all these predictors. But then the cases that are dropped due to missing data, say the rare category was 1 out of categories 1 and 2. The cases that are dropped deleted all the instances of category 1. All the cases that were in category 1 had some kind of missing data. So everything that's left for the complete cases is only category 2 on that variable. That's going to give that error.
Yeah. In R, we can do the SVY by and show the missing.
No, that's just a descriptive task. It has nothing to do with surveys.
Yeah,
You just have to go variable by variable and see what the culprit is. Yeah, it's a missing value issue. Yep.
And
No, I'll ask through the email. I just have to think about my question.
Okay.
I need to organize.
because the bootstrapping data to set the design and put the replication, I think
I just didn't get the Roscoe F test results when I do the bootstrapping on Stata. So I wanted to check on the.
Yeah, I'm not sure why that would be. Okay.
I'll try to troubleshoot it.
Okay, yeah, that sounds good. Okay, let's pick up again here and see who's outside.
I think
Okay. All right, so we've talked about multinomial and ordinal. Let's shift our attention to Poisson regression within Stata. So now we're revisiting that analysis in the health and retirement study data, where we look at the number of falls within the past 24 months using the HRS data. So that's our specific count outcome. So we're going to start here by reading in the HRS data that's up on Canvas. And again, shifting all the names to lowercase. All right, then we're creating a 3-category version of age, being careful about missing data. Okay, so if I run this analysis here, I do see that there is in fact one missing value that would have been mistakenly recoded as a 3 if I had not been sensitive to missing data on the original age variable. Okay, so now I have that 3-category age variable with missing values correctly handled. Now I set the survey design variables for the HRS, which in the 2012 wave were N, that the weight was N, so N weight R and N weight HH. Then I have the CQ variable for the cluster codes and the stratum variable for the stratum codes. All right, so I'll set those design features for HRS. Now we'll look at that histogram of the distribution of number of falls like we did in lecture, specifically restricted to people who are age 65 and above. Okay? And remember in Stata, when we make a histogram, we have to use F weight as opposed to P weight. So it doesn't like decimal weights in that particular command. So this is just going to round the weights, not making a huge difference in the end result of the histogram. So this is looking at the population estimate of what that distribution looks like. And you can see very similar to what we saw in class, a preponderance of zeros, okay? And then the distribution kind of tails off 1, 2, 3, 4, 5, et cetera, with some cases having an excessive number of falls in the past 2 years. Yeah. So that creates that weighted histogram of that count variable. Here, this is just to demonstrate, if we look at a cross tabulation of the sample design codes, and then we restrict it to cases age 65 and above, there is in fact one HRS stratum that had nobody above one HRS cluster within a stratum that had nobody above age 65. And remember in Stata, survey describe will show you that with an asterisk. So what this is telling me is that if I used a conditional analysis, right, linearization would break down for that particular stratum because I only have one cluster present.
So I have to subpop.
Subpop. All this is saying is all I've been saying all along. Just make sure you use subpop. That's all. But this would be the case if we had, if when we were using the commands, we mistakenly kept saying if, and being conditional about what we were doing, we'd run into a problem with linearization. Okay, so that's the key point. Okay, here's where we can look at that distribution just in terms of raw counts of number of falls, and you get a sense of what this looks like. 64% of the data set has a 0. So it definitely seems like there could be a zero inflation process going on here that we might want to model. Only 13% to begin with have a 1, have fallen at least one time. So falling is a relatively rare event, but it's still a discrete count in the way that we want to model it. And then there are certainly some extremes. 50 being the maximum that somebody could have said. Now we want to interpret everything in terms of rate per month, like we did in the lecture. So we're creating a new variable called offset 24, which is going to be equal to 24 for everybody. By default, everybody would be assumed to have the same observation period of 1, which would be 2 years in this case. So you'd be modeling the rate every 2 years. We want to talk about what happens to the monthly rate. So to do that, we add an offset variable equal to 24 for everybody for these counts. Okay. So that's just creating a variable that's a constant for everybody in the data set, that generate statement. Okay. Now that we've done that data prep, we can use SVY Poisson or SVY MB-Reg. Yep. Poisson fits the Poisson regression model. MB-Reg fits the negative binomial regression model. And we're including all the zeros as part of the distribution. I posted an announcement about that assumption of the distribution. Okay. So here, this is not zero inflated. These are just the raw, the classic Poisson negative binomial models. So I just list the count dependent variable first, then the predictors with any reference category specified. Then IRR asks for exponential versions of the estimated coefficients. And exposure is where I put in that offset. That says everybody has an exposure period of 24 months. So it's going to use that to compute monthly rates as opposed to a rate every 2 years, which would be the default. Okay. So thinking back again to my announcement about the Poisson distribution, adding the exposure variable adds T to that parameterization. Leaving the exposure variable out just leaves everything as lambda. You're looking at the overall rate. Okay. Okay. So let's see what happens when we fit the Poisson model. I'll highlight that first command. Okay, so what we're seeing are these estimates of the incidence rate ratio, or IRR, just the exponentiated versions of the coefficients. So gender equal to 1 is for males, okay, gender 2 is for females. So what would be our interpretation about the monthly rate if we're comparing males to females? Remember, this is a rate ratio. This is the exponentiated version of that estimated coefficient. So in the Poisson model, we're talking about a ratio of rates. And here we're talking about males versus females. So what would our interpretation be? Remember, we're talking about the monthly rate of falling because we're using that offset of 24.
The monthly base is about 30%.
30% what?
Higher.
Higher.
Higher, yeah.
Right. So the monthly rate of falling is about 30% higher for males compared to females. Okay. What about age categories? It's a lower monthly rate for the youngest people as opposed to the oldest people. Okay, lower by about 24%. Okay. What about diabetes and arthritis? Diabetes increases the monthly rate by 29%. Arthritis increases the monthly rate by about 111%. Okay. Same way we're thinking about odds ratios, we're just talking about rates. Okay. The count at the rate at which this event occurs in a monthly period per month, because we're using that offset of 24. Okay. Okay. And then it's just, you get a reminder that you have this offset variable in the model with a coefficient of. Now, let's see in contrast what happens when we do the same analysis, but now using a negative binomial model that lets the variance be larger than the mean when fitting this particular model. Okay. Okay, estimation again, pretty quick. The estimates, the weighted estimates, the rate ratios look very, very similar if you line them up. Okay, so we don't see a huge difference. But one additional point that gets estimated, here's this alpha parameter. So this is what I was talking about in lecture. You get an additional weighted estimate of that alpha parameter that inflates the variance relative to the mean. Okay? So if that alpha parameter was 0, that's evidence in support of using the Poisson to make your inference. Okay? Looking at the confidence interval for that parameter, not even close. Okay? So this is that justification if you're picking between these two models to model a count that says allowing for more variance than the mean would suggest for that distribution makes a lot of sense, even though the inferences are very similar. Okay? So ultimately, if we're debating between these two models, we'd probably choose the negative binomial model, assuming that we had evaluated all our predictors and everything else. Okay? Seems like the better matching distribution for this particular count. Okay, so those are the classical Poisson negative binomial models that don't handle the zero inflation. Okay, they're not trying this two-part model where we're seeing this excess count of zeros, and we'd like to try to understand if there's a process that leads you to never fall. And then among those who actually do fall, let's see what the important predictors are. So another note that I posted on after Wednesday, where I messed up that the way Stata is fitting that model. The logistic model is actually modeling the probability of 0 on the count variable. So what's the probability of never falling? Okay, so that's what that part 1 logistic model is doing. All right, so here we're trying a zero inflated negative binomial model. Okay, so the command to do that, accounting for the design, is SBY:ZINB, zero inflated negative binomial. That's something that just does not exist within R. Okay. Same model set up for the substantive model, but remember, that substantive model is for the people who have fallen at least once. Okay. So we're looking at predictors of how many times you fall for the people who have ever fallen at all. Okay, that's in the substantive part of the model. The inflate part of the model is a logistic model for the probability of never falling. That's what I had backwards on Wednesday. So we're modeling the probability of a 0 on the count. Same model approach, just different interpretation of the odds ratios. That's all. Okay, so we're still getting rid of those excess zeros conditionally by including this as part of the overall process. All right, so we get those predictors in that logistic model from the inflate option. So inflate, in parentheses, include whatever predictors you want to include. When I was fitting this model and preparing the lab notes, I had a lot of convergence issues when I added more and more predictors to the inflate model. Okay, and we're going to look into why that's happening in a second, but that can happen, and you may have to reduce the number of predictors in one or both. Ideally, you want to try to find unique predictors of never falling before looking at your overall substantive model. So here, I'm just using arthritis. Okay, the rest of the command is the same for the negative binomial options. So these zero inflated models will take longer to fit. Okay, so this is a definite thing. It's a harder likelihood to maximize, more parameters being juggled. So when I run this, I can't assume that I'm going to get results right away. Okay, this is one of the more complex models that we're fitting, okay? And this machine went pretty quick, didn't go as quick on my work machine. The point I want to make is that if you're using replication or bootstrapping or something like this, we're getting into the kinds of models now that can take a fair amount of time to estimate. And this is where we have to think about whether a replication variance estimation approach makes sense, just from a computational perspective. Okay. So looking at the zero inflated model, notice that we have these kinds of two different sets of output. Okay. Here is the substantive model among the people who have ever fallen at least once. Here is the logistic model for having zero falls. Okay. And basically what we're seeing here is that arthritis is almost a perfect predictor of whether or not you've fallen before. Okay. So here, if you've had arthritis, the probability of having zero falls skyrockets down. Okay, that coefficient is -28, which is huge. Think if you were going to exponentiate that, right? It's basically saying that if you have arthritis, like you're almost guaranteed to have fallen at least once. Okay, so there's a huge negative relationship. And again, you could include other predictors in that logistic model so long as the model converges. I was running into issues when I was playing around with that. And again, in the zero inflated negative binomial model, you'll get the estimate of the alpha that provides support for using that over a competing zero inflated Poisson, for example. So the fact that arthritis is an important predictor of zero inflation means that this would probably be a reasonable model to choose over and above the classic negative binomial model. Okay. So this can be really helpful because again, these zero inflated models, they answer two research questions at once. So what predicts the probability of never falling versus falling at least once? And then among those who have fallen, what predicts the probability of how many times you're going to fall? And you see similar patterns of results, but the associations are not as strong as they were before. Okay. Okay, so those are the options for modeling count data. As I mentioned in class, there aren't really good kind of GOF commands or various goodness of fit tests for Poisson models at this particular point in time, but you can still save predictions of the counts and compare those counts to the actual observed counts in the data to see if there's reasonable agreement of predictions based on these models. Just remember that if you're doing that kind of diagnostic based on a zero inflated model, you want to line up those predictions for those cases that have fallen at least once, because those are the cases to which the substantive model applies here. We're getting rid of the zeros. Right? So just keep that in mind when you're lining up your predictions.
So there is a note there. See that the second part, is it log scale, the coefficient?
It's log odds. So it's just like a logit model. That's what I'm saying. That coefficient is massive in magnitude. Yeah. And the additional syntax that I added to the lab notes here, just to kind of understand that in a little bit more detail. So I created a variable called any falls, which is 1 if they've ever fallen. And notice I'm again being careful about missing data to code that variable. And it's a 0 if they've never fallen. And then I'm looking at a crosstab of arthritis with any falls and just looking at row percentages, specifically for people ages 65 and above. Subpop. So if I create that variable and do this analysis, I basically see there's a big difference in ever having fallen, depending on whether or not you have arthritis. That Rouse-Scott test is significant at the 0 level. So that's just where that large relationship is coming from in the overall inflation. So that's a good thing to check. Okay. Okay, so that's what I want to say about Poisson and negative binomial. Questions about those modeling procedures and Stata? Any questions about how we're using those? Questions, comments? Okay. Okay, let's turn to R, if there are no further questions. Again, we're going to be a little bit more limited in terms of what procedures are available, but we'll see the analogs of what we were trying to do here. So again, I'm loading the relevant libraries that I need for these particular analyses. We're going to come back to another library we need later on. So Tidyverse, Survey, and Haven for data management commands. I'm reading in the NCSR data from my working directory and creating labels for each of my categorical factors. So I'm going to run all of this at once. All right? So now I have all my categorical factors declared as such with reasonable labels. I'm setting my design features for the NCSR, the survey design object. Okay. Can summarize it if I want. Right, so familiar with that kind of breakdown of the PSUs and clusters at this point in the NCSR. Now, remember that there's no multinomial modeling option within the survey package as it currently exists. To find the multinomial modeling option and still be able to adjust for the design features, we have to load this SVY VGAM library. Okay, and remember, to load a package, you have to first install it. So in our studio makes it pretty easy to do that. I can just go to packages over here, install, look for SVY VGAM, install all the dependencies as well. Okay, so it'll take a little second. Once I have it installed, then I can load that package and the functions will be available to use. Okay. So now I've installed that package and I have loaded the functions that are within that package so that I can use them for this analysis. Now, to fit the multinomial model, I would use SVY VGLM. And that function is only available in SVY VGAM. It's not available in survey. Okay, so I want to just emphasize that point if you need to fit a multinomial model within R. And the way that SVY VGLM works, very similar to what we've seen before, but for a multinomial model, I'm making sure that everything is treated as a factor, including the dependent variable. So I say as.factor, then the name of this variable to make sure. I have my factors listed among the predictors. I have my design object. And then in the family argument for this model, I say multinomial, and then you declare a ref level based on either your string labels or your numeric values of that dependent variable. So here I'm saying I want the reference level to be employee if I want to change that on the fly. Remember in Stata we were using not in the labor force. So I could change that to be the label that I use for not in the labor force, which I believe is NLF. But that's how you set the baseline category within this SVY VGLM function. Okay, everybody with me so far? Other than that, the function looks very similar to the other modeling commands we've been using within the survey package. Okay, so I will go ahead and fit this model. Okay, again, the multi-level model might take a little while to estimate. Let's look at a summary of that multi-model object. Okay. So the way that R approaches it, right, you have logit 1 relative to employed and then logit 2 relative to employed. A little bit tricky to navigate this output because technically those are categories 2 and 3, right? So it's just referring it to in sequential order the logit that's being estimated. It also puts the same coefficients together right next to each other, as opposed to giving you separate sets of output for each logit. So that too can make it a little bit challenging to navigate when you're looking at the output. So the estimated coefficients in that first logit, which would be 2 versus 1, so unemployed versus employed, you'd find those here, here, basically every other line in the output to extract those particular coefficients. So you could write a little bit of code to pull those out of the object here containing all these modeling results, but just takes a little bit of navigation. Okay, so you see separately for each of those two logits, each of these different coefficients in the multinomial model and their corresponding p-values. Okay. Now, no M-logit GOF, anything like that within R. You'd have to exponentiate these coefficients and their confidence intervals to get odds ratios and corresponding confidence intervals. So there's a little bit of extra work. It's not as pretty as the Stata output was, but ultimately you can arrive at the same model using this combination of functions in this case. Okay. Yep, here.
So I have a question on
Yep.
multinomial and odds ratio.
Yeah.
So like when I check the book, so like to get the odds ratio, we exponentiate the log odds, no?
Right.
And then to get the confidence interval, we exponentiate the confidence interval. But I was wondering, how do we get the standard errors?
Yeah, the standard errors, you have to rely on the software to compute those. There's no easy transformation. If you want to report a standard error for an odds ratio, like that's what SVY logistic is giving you automatically in Stata. Like you're not going to get that out of R. R is only giving you the standard error on the log odds scale. Yep. So it can be done. In this case, you're just asking the software to do that. That was actually, it's funny you asked that, Kier. That was a question on my qualifying exam. Like compute the linearized standard error of an odds ratio. So yeah, that gives you a taste of what we're studying.
An additional thing is like I saw in stock exchange like last week, Frank Harrell mentioned that odds ratio, the standard error of odds ratios are not useful for getting the confidence interval.
No. Yeah. Because again, the confidence interval is going to be based on the limits on the coefficient scale. So the standard error of the odds ratio, not really clear what it should be used for. You can compute it because it's a statistic, but not really clear what it should be used for. So when I got that question on my qualifying, I was like, okay, I'll spend 30 minutes doing this, but what are we doing it for? Hey. Okay. Other questions about the multinomial approach in R? The key thing here is just getting this additional package and then navigating the output. Okay, ordinal. Here within NCSR, we're looking at this obese 6CA variable. So I get a sense of the overall distribution within each of these ordered categories with that table statement. Here I can check the different proportions with different obesity status using the population weights. Remember that survey mean is how we get estimates of proportions in different categories. We just have to be working with a factor. So in this case, that's obese 6A. So you see the estimated proportions within each of those categories and then the, corresponding standard errors. Okay, we can generate a bar graph of those weighted estimates of the proportions if we want. Okay, so here I'm saving those proportions in a new object called OBSE. Okay, and then I'm using this bar plot option to plot the information within that OBSE object. That's one way I can create weighted bar plots within R. Okay, so I'm going to go ahead and run this piece. I just need that OBSE object to begin with. So again, not beautiful at the beginning. I can play around with this a little bit, play around with the fonts, play around with where I put the legend, but you see the basic idea there. I can use the information generated by survey mean to create this histogram, or not histogram, but bar chart of the weighted proportions within each of these categories. Okay, now ordinal is within the survey package. So the survey package contains this SVY OLR function that you can use to fit ordinal models using that proportional odds assumption. So that's the key point here, is that when you fit this model by default, it will use the proportional odds assumption, but there's no easy way to test it, allowing for the complex sample design. That's why the geologit2 command is so useful within Stata, is that we can test that assumption incorporating all the design features. We don't have something like that within the survey package. So in the SVY OLR function, it's actually really simple to use. We just declare our model formula, and I'm reminding you here how you can set a reference level on the fly for a categorical predictor, and then just declare the design object. Okay. Everything else will be taken care of by the function itself. So I'll fit that model and then look at a summary of the resulting object here. Okay, so you see these weighted estimates of the coefficients on the log odds scale under the proportional odds assumption, along with the estimated cut points. Okay. And again, if I want to double check that everything is in the expected direction, I can refit that model using SVY GLM, which by default fits the linear regression model. Okay. So if I'm not positive how R is parameterizing that ordinal model, is it using a minus sign like Stata used? Is it using a plus sign? Let's just fit the same linear regression model, look at that summary, and see if the coefficients are in the same direction. So if I look at age, positive in the linear model, positive in the ordinal model. If I look at being a male, positive in the ordinal model, positive in the linear regression model. So that tells me that R is using the same parameterization as Stata. in terms of using a minus sign in that proportional odds model, where a positive coefficient means that you have higher odds of being in a higher value category on the dependent variable. Okay, so same kind of output that we saw in the statement. But that's always a good check just to make sure you're reading the coefficients in the right direction. Okay, and if you wish to obtain odds ratios, we can exponentiate the estimated coefficients in the ordinal model. Okay, so that's just giving me all the odds ratios that I'd already seen previously. And again, we can use reg term test. So here is giving you the analog of using test with MDE and sex male that we use within ordinal regression in Stata. So this is testing whether that block of predictors is adding anything to the overall model. Okay, so I can use that reg term test, and just like we saw within Stata, we would clearly reject the null hypothesis that both of those predictors have coefficients of 0 in that model. Okay. Okay, so again, unfortunately, no design adjusted version like GeoLogit 2 to test that assumption, but that's how you would fit these ordinal logit models within the survey package. Okay, so there's definitely some work to be done there in terms of model evaluation and so forth. Okay, finally, we can use Poisson regression also via the SVY GLM function. So what I'm doing here with Poisson regression, I'm reading in the HRS data into a new object, resetting the names, creating my factors, and then looking at a table on the new age category variables. I'm going to go ahead and run all that. And there I see my one missing value, making sure that was handled appropriately. Okay. Declare the HRS design features. This new survey design object called HRS survey. Okay. Double check, make sure that looks good. Then I create, remember in R, if I want to work with a subpopulation, I have to use that subset function applied to the survey object. Okay, so I'm subsetting HRS survey to be for those who are age 65 and above, creating a new design object for those folks. All right, so that ensures my unconditional analysis. Here again, you can note the missing strata and SICUs if they apply. Here we see the actual number of PSUs was 1 in that particular stratum, okay, just like we saw within survey described. Here we are making a survey histogram where we're just using the design object as it is. We don't have to use an F weight like we did within Stata. We're just using the design object as it is and looking at a histogram for a number of falls in the past 24 months. So that's an advantage of R over Stata. We're not rounding the weights. Okay, so I'll use survey hist to create that graph. And there you see the same thing we were looking at in lecture and in Stata. Okay, this is the weighted distribution on that count variable showing the large number of zeros. Okay, and then we can fit a Poisson regression model using SVY GLM with the quasi-Poisson family and a log link. That's how we set up the Poisson regression model within SVY GLM. Okay? That particular family choice with a log link. Other than that, the model itself looks similar to everything we've been doing thus far. Dependent variable on the left side, predictors on the right side separated by pluses, the design object, and then the family that we want to use. So Poisson regression is another family within survey GLM that we can reference. So I'll fit this model, same model we were fitting within Stata. And here again, we're getting that warning, okay, that there are some cases with 0 weights in the HRS data. Then we can summarize that model fit object. Okay, so these are on the log scale. So by default, R is showing you the coefficients on the log scale. So if we want to calculate those incident rate ratios, we do have to exponentiate those coefficients. Okay, so here's how we would exponentiate those coefficients to get those incidence rate ratios, and we're back to what we saw with it for the odds or for the rate ratios. All right, so we could do that to the confidence limits, whatever else we wanted to exponentiate to get back to inference about those rate ratios. All right, so we can fit a Poisson model, but again, there's no negative binomial option. All right, so we don't have that kind of luxury within R as well if we want to consider competing models where the Poisson mean equal to variance assumption might not hold. So we're kind of limited at that point. And as of right now, there are no zero inflated commands. Okay, so that's definitely an advantage of Stata over R if you want to fit those two-part models, you have a large number of zeros. So our hands are a little bit tied in terms of what we can do with this distribution right now. Honestly, with this number of falls, I'd fit a logistic model, just looking at 0 versus 1. I mean, we're illustrating count models in this case, but I look at 0 versus any falls and focus the inference on that to find what the most important predictors are in this application. Okay. Okay, so that's what I wanted to illustrate in terms of what's available in R right now for fitting these different generalized linear models. Questions, comments about what we just went through in R? Questions, comments, thoughts? Yep, Isaac.
I have a question regarding F pairs.
Say louder, Isaac, I can't hear what you're saying.
I have a question regarding F pairs. We are using F pairs for this.
The F verse?
F pairs.
Weights.
Oh, F weights. Okay, gotcha.
So we didn't use like the combination pairs of the pairs. Why we are using F pairs?
Just simply because in Stata, the histogram command doesn't accept p weights. So the way that command is working, it will only take integer valued weights, whatever kind of weight you're inputting. Here, survey hist is designed to analyze decimal weights. So it's just a limitation of what's available in Stata right now. Other questions about the code here for R? Okay, I think we are all set for today then. So definitely I'll be trying to keep an eye on email over the weekend. If people have any kind of urgent questions about your results or anything for the final project. So make sure to send us a note and CC Young Chow in case I don't see it. But we'll look forward to seeing your drafts. And again, you can submit those by 5 o'clock on Monday. Don't have to submit them by the 9 o'clock hour in the morning. And please do submit them by email. Okay, so there's no assignment for the drafts in Canvas. Okay. Okay, if there are no further questions, I think we are all set for this week. I want to wish everybody a good weekend, and we will look forward to seeing your drafts on Monday. Okay, thank you. Newman.
5 o'clock means like 9 AM because we have hours and after the workshop, like we free at 5 PM.
Thus is the life of the sampling program. It can be 5. We just want to get started on the review. So you should not be at a point where you haven't written a word for this project. Like you should be at a point where you're spending this weekend proofreading. Yep.